Alright, let's take a look at a couple of other examples. Here take a look. Stephen made a conjecture that the difference between consecutive perfect squares is always an odd number. Hey, that's the same conjecture we came to when we looked at the difference between consecutive perfect squares. Francesca's conjecture was that the difference between consecutive perfect squares is always a prime number. How can these conjectures be tested? Well, let's take a look and do a systematic look at the pattern. Alright, so let's see. We did 4 minus 1 is 3. Right? For Stefan and Francesca, it confirms both of their conjectures. Let's see, next. 9 minus 4 is equal to, or 9 minus 4. 9 minus 4 is equal to 5. Right? That works for Francesca. It also works for Stefan. Next, see, 16 subtract 9 is equal to 7. Again, that works in both Stefan's conjecture and it works in Francesca's conjecture. Right? Odd number for Stefan, prime number for Francesca. Odd number for Stefan, prime for Francesca. Let's take a look at the next two. 25 minus 16 is equal to 9. That's an odd number, but 9 is not prime. Right? That is a counterexample to Francesca's conjecture. Alright, so Stephen's conjecture is better so far than Francesca's. Her conjecture is not true. Stephen's, on the other hand, so far the evidence points to it being true. Alright, now let's take a look at this next sequence. It says Matt found an interesting numeric pattern. 1 times 8 plus 1 is equal to 9. 12 times 8 plus 2 is equal to 98. 123 times 8 plus 3 is equal to 987. 1,234 times 8 plus 4 is equal to 9,876. Matt thinks that this pattern will continue. Search for a counterexample to Matt's conjecture. Well, let's start. 1, 2, 3, 4, 5 times 8 plus 5. What do we get when we do 1, 2, 3, 4, 5 times 8 times 8 plus 5? Well, look at that. We got 9, 8, 7, 6, 5. Right? It's interesting. Looks like the pattern's continuing. We might as well keep going. Let's see. Taking a look on our calculator, we have 1, 2, 3, 4, 5, 6 times 8 plus 6. Well, I'll be 9, 8, 7, 6, 5, 4. How long do you think this will keep up? Sometimes searching for a counterexample takes some time. 1, 2, 3, 4, 5, 6, 7 times 8 plus 7. Well, still working out. 9, 8, 7, 6, 5, 4, 3. 4, 5, 6, 7, 8 times 9. Oops, times 8 plus 8. Alright, putting that on the calculator. 1, 2, 3, 4, 5, 6, 7, 8 times 8 plus 8. So far, so good. 5, 4, 3, 2. 1, 2, 3, 4, 5. Whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9. times 8 plus 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 8 plus 9. Keeps working. So far our patterns worked. But now 1, 2, 3, 4, 5, 6, 7, 9, 0. What should we put here? Should we put 0 there? Probably not. We should probably put 10 times 8 plus 10. 1, 2, 3, 4, 5, 6, 9, 10 times 8 plus 10 gives me something like 9, 8, 7, 6, 5, 4, 3, 1, 2, 9. And our pattern breaks. That right there is our counter example. So, in conclusion, we've got this idea of a counterexample. And a counterexample is a piece of data that doesn't fit our conjecture. Right? If we find a counterexample, we have to make a new conjecture. Reject the old one, come up with a new one that fits all of the items in our data. Alright, to take a look at counterexamples, your assignment is on page 22 to 25, numbers 3, 5, 8, 10, 12, 14, 16, 17, and 19. Excuse me.